and I'm going to talk about not the specific language features, but what did we do to actually implement them? What does the bytecode look like? What were the challenges? What were the interactions between the VM work and the compiler work? So it's hopefully, how many people here have used like the Java P tool to dump bytecode out? Some of you, okay. How many people here have used ASM to produce bytecode? Okay, some of you, all right. So that's basically the level at which I'm going to be talking. I apologize for not having reformatted my slides using the JAX template. So, like I said, technical details of how do we do this, and hopefully with some background on why we made some of the decisions we made. There will be a little bit of overlap, a couple of slides that are in common from the last talk, so bear with me for the redundancy. How many people here also are familiar with the work that went on in JSR 292, invoke dynamic and method handles? Just a few people. Okay, so I'll go over those in a little bit more detail. But basically, it's a good story of eating our own dog food, right? So in Java 7, as part of JSR 292, we upgraded the VM in ways that were completely invisible to the user, but offering services and facilities for language runtimes and compiler developers. In particular, we added some facilities for low-level representation of composable behavior. You can think of that as a VM-level representation of closures, and also a way for language runtimes and compilers to get more involved in linkage decisions that are made by the VM. As a result, languages can take advantage of these facilities to more efficiently implement language concepts. And the sort of hidden surprise is, even though invoke dynamic has dynamic in the name, and our original intention was this was mostly for dynamic languages like Ruby and Python, it turns out that Java is going to be one of the biggest beneficiaries of that. So, like I said, a little bit of repetition here for those of you who missed the last talk. A Lambda expression or a closure is an anonymous method. It has everything a method has. It has an argument list. The arguments have types. It has a return type. It has a body. It has a list of thrown exceptions. The one thing it doesn't have is a name. And the idea is, it's a way of representing a little bit of behavior that you can treat as data. You can store it in a variable. You can pass it to a method. So, for example, people.forEach, take the person, get the name, and stick it in a collection. We've done a lot of work in the compiler to make this syntactically more pleasant, not only compressing down the syntax, but adding a great deal of type inference. So the compiler is fully able to infer the fact that E in this example is a person and not make you type it out. Again, this is not dynamic typing. This isn't turning Java into Ruby. It's simply the fact that the compiler is smart enough to know that the only thing E could possibly be here is a person, and it's not making you type it out by hand. And Lambda expressions, the body of a Lambda expression, can refer to names that are defined in the lexical context of the Lambda expression. In other words, from outside the Lambda expression. So you can say, remove all the people from this collection who are younger than some minimum age, where minimum age is a local variable or field defined in the lexical context of this statement. Okay, so these are the language concepts that we're adding, and so what this talk is about is how did we do that. So, a little bit of a repeat again from the last talk. Why are we doing this? Lots of reasons. One is keeping up with the competition. One is providing libraries a path to parallelism. Another is providing more effective libraries. You could observe that, well, we did this 15 years ago with inner classes in 1997. Wasn't that enough? Really, are we adding anything new and radical? And the answer is yes and no. Inner classes had the same motivation as this. they were clunky, and they were clunky not just syntactically, but they were clunky in a number of ways. They're clunky in terms of how name resolution works inside an inner class. That the meaning of a name could come from the lexical context, or it could come from the superclass hierarchy. So you have this very complicated and easy to get wrong name lookup algorithm for what does a name inside an inner class mean. And that was a difficult thing to reason about. Inner classes are fundamentally objects. They have identity. That's something that gets in the way of the VM being able to optimize effectively. And similarly, the way that we're represented in bytecode, we statically generate a class that could get out of sync with the enclosing class, and some really bad things can happen. So you can think of inner classes as a good first attempt. We limped along with them for 15 years, and now it's time to do something better. So how we would represent Lambda expressions at runtime is a difficult question, a lot of options, definitely not a trivial thing, and that's basically what this talk is about. So the first question that you have to answer is, okay, we're adding a new kind of expression to the Java language. What is the type of that expression? And like I said earlier, in most languages, they already have a concept of function type. So a Lambda expression would have type of some function type, function from string to int, or something like that. So Java doesn't have one of those. We could add one to the language. But more importantly, the code generated by the compiler has to map to something that the VM can run. And the VM has no native representation for a function type either. So if you look at VM type signatures, you can refer to primitives, you can refer to classes, and you can refer to arrays of primitives and classes. And that's it. That's what we have in the VM. So if we said, all right, what we should do is add function types to the VM, well, that opens up a whole set of new questions. What would these signatures look like? How would we create instances of them? What about question extends and question super? How do we represent those in the VM? How do we teach the VM to reason in this much more complicated type system? What will be the performance consequences of that? That is a rat hole, and we wanted to avoid that. And so given that we didn't want to do significant VM changes, we looked at alternatives. One alternative would be to represent function types as generics in the compiler, but that kind of would stink as well because then they would be erased. So we went around looking for other alternatives, and we found one from history, which is historically we've modeled behavior using single method interfaces. The library is full of interfaces like comparator, runnable, callable, action listener. And so rather than go like type system crazy, which is really fun, we said, let's just keep doing what we're doing. Let's formalize the concept of single method interfaces. For a while, we were calling them SAM types, where SAM stood for single abstract method. Sometimes you'll see that acronym. We're giving them a slightly more geeky name, functional interfaces, but it basically means interface with one abstract method. And then we adopt the rule in the compiler that says you can only use a Lambda expression in a place where a functional interface type is expected. And that turns out to be not a significant restriction at all. So here's an example of a functional interface. Predicate of t takes a t, returns a Boolean. So you can think of this as isomorphic to function from t to Boolean. And then we have this new method in collection, remove all, that takes a predicate of t. And so we can say people.removeAll, p maps to p.getAge is greater than or equal to 18. And the compiler figures out the types, the compiler figures out that p is a person here, and then the Lambda is converted to a predicate of person. So, all right, how do we do that, right? So we have this syntactic construct in the language. We have an idea of what type it is, but we have to, since we're going to pass it to the library that's expecting an actual object that implements predicate of t, we need some way of actually affecting that conversion. Okay, so let's look at some options that we considered. The obvious first choice is just use inner classes. So we could do this very easily. We could have actually, if we had chosen this path, we could have been done in 5 minutes and gone home, and the compiler already knows how to spin out inner classes. It's really simple. So if we were converting this lambda, to a predicate, we would generate a class, make up a stupid name, foo$1, implements predicate of person. It needs a field to hold the captured value. So we give it a field. It needs the constructor to initialize that field. So we pass the captured value to the constructor, and then the body of the test method is almost identical to the body of the lambda. So really easy. Like I said, we could have been home by 9:30. But we didn't want to do that. And we didn't want to do that for a number of reasons. One is the fact that inner classes spew hundreds of small classes into the file system and have to be loaded individually is kind of annoying to people. So we didn't want to carry forward that restriction of inner classes as a permanent choice. We would have been stuck with the one class per lambda expression restriction, which also has a problem for the VM, because if we have a zillion implementations of runnable, that means call sites that invoke runnable are likely to be megamorphic, which gets in the way of a number of VM optimizations we would want to be able to do, such as inline caching or inlining. So we sort of viewed this as an opportunity to get rid of inner classes. The good thing about doing inner classes not only would it be simple, but like the invocation is also simple. The compiler just translates the inner class, the lambda expression to calling the constructor of our new inner class, and we're done. So that would have been nice, but like I said, has some disadvantages. And just to take a look at the bytecode for what that looks like is also pretty straightforward. Push the list on the stack, create a new foo$1 instance, pass min age to the constructor, call the constructor, so now the predicate is on the stack, and then we invoke the remove all method, receiver's here on the stack, predicate is here on the stack, and we call this static method. So would have been straightforward, but like I said, we didn't want to do that. So problems of inner classes include one class per lambda, pollution of type profiles, like I said, lots of instances, lots of different subtypes of runnable lying around, plus the linguistic complexities of the horrible way that names are interpreted in inner classes. But the bigger reason we didn't want to do this is we didn't want to commit to this for forever. And unlike what other languages do, where how many people here do some work in Scala? How many people here are frustrated by the fact that every time the Scala language gets updated, you have to recompile everything? Right? That's pretty annoying. That's a real, screw you to your users. So we don't do that, right? We have made this commitment that your bytecode will work forever. Bytecode that was compiled with a previous version of the Java compiler should continue to work forever. Okay? So if we were to choose to represent lambdas as inner classes, we would implicitly be choosing that inner classes are the binary representation for lambdas in Java forever. And first of all, I don't think it's a very good implementation. Second of all, this is an unfortunate conflation of an implementation detail with a binary interface. So we don't want to do that. So let's talk a little bit about bytecode. In the workup to Java SE7, the lead up to SE7, we had 4 bytecode operations available for invoking methods. Invoke static, invoke virtual, invoke interface, invoke special. Obviously, invoke static is for invoking static methods, invoke virtual is for invoking class methods, invoke interface is for invoking interface methods, and then special is a sort of like the garbage can of everything else. Constructors, super methods, private methods, etc. What they have in common is at the invocation site, they have the name of an enclosing class, the name of a method, and a signature. And they all have that, right? That's common to all the invocation modes. And this will be important when we look at some of the other options that are available to us. Okay, so in Java SE7, we added a new set of bytecode, a new bytecode. Getting ahead of myself. Rewind. We added a new mechanism for compiler developers to represent behavior called method handles. So this is, there's a set of library classes called method handle, and there is VM support for method handles. So you can think of a method handle as being a VM level closure. And you can store references to methods in the constant pool of a class, and you can use the load constant bytecode to say, load me a method handle for this class. And this is a very fast operation. So you can basically load a pointer to a method right into a register that way. And because and you can do this for any kind of method, a static method, a virtual method, a super method, even field access. You can turn this into a field getter or setter. You can turn this into a method handle. And the nice thing about this is that since the VM knows what a method handle is, it can inline through them. It sees, when you do a method handle invoke, when it builds its intermediate representation before it goes and generates machine code, it says, oh, I know that that's really a method handle invocation. I can trace the trail of breadcrumbs back from the invocation to where it was loaded from. If it was loaded out of a constant, I can just generate code to just call that directly and get rid of the overhead of the method handle manipulation. So all of these combinators that are in the library that look like library code for adding arguments and removing arguments and reordering them, and adaptations like boxing, unboxing, var args, collection, casting, composition, all of these things look like, oh my God, the code for this that it would generate would be so nasty. In fact, the code for that it generates is like beautiful because the VM knows what all that stuff does, and it just generates the bytecode that you meant, and it's really great. So as a compiler writer, this is great. This is your Swiss Army knife. You can slice and dice functionality and compose it and do all those nice things, and the VM knows exactly what to do with it and generates beautiful code, in theory. Okay, so just like we said, why not just use inner classes? We might say, well, all right, why not just use method handles? Method handles are like a VM level closure. Lambda expressions are a language level closure. How could this not be a match made in heaven? So this seems like an obvious first choice, and all we would have to do this is take the body of a lambda, turn it into a method, desugar it into a method, and then if we have a method that takes a lambda, translate that as a method that just takes a method handle. And we're done, right? And so we're maybe not done in 5 minutes, but we might be done in a few days. The compiler behavior would be fairly straightforward. If we're translating this bit of code, we'd say, okay, let's turn this lambda expression into a separate method. We desugar it into a private static method. It returns a Boolean because predicate returns Boolean. It has an argument for person, and it has an extra argument for this captured value because min age is captured from the context. And then the body is translated directly from the body of the lambda expression, and to call it, all we do is say, load me up the method handle for this method, stick on this captured argument, min age, and pass it to remove all. So we could have done that, and that would have been really straightforward also. So why didn't we do that? Well, if we did, the VM representation of remove all would be, I take a method handle. Method handles are untyped. They're actually strongly dynamically typed, but they're completely untyped statically. So this is taking erasure, which is already a problem in Java, but a problem that we mostly can work around, and making it just much, much worse. So for example, if you had two remove all methods, one that took a predicate and one that took some other functional interface type, the compiler would tell you, sorry, you can't overload these methods. They both have the same erasure. And you'll look at the type signatures and you'll say, how could these two things possibly have the same erasure? So it would be extremely confusing to users. So while it's a nice representation and we will use method handles under the hood in the implementation, we don't want to bubble them all the way up to the level of VM type signatures. So again, this problem, this approach, which seems just as obvious, or maybe slightly less obvious, but almost as obvious, as the just use inner classes, has the same problem, which is conflating the binary representation of lambdas in bytecode with a convenient implementation detail that, that we happen to have chosen. Okay, so let's take a step back. We tried two different approaches both of which seemed obvious, both of which had pros and cons, and which we rejected both of them partially on the basis that we wouldn't ever get to change our minds. We had to pick something now and be happy with it forever. So we rejected interclasses because they have baggage. We rejected method handle because it was too low level. And we're not willing to force our users to recompile. So every problem in computer science can be solved by another level of indirection. So let's do that. And you might think at first that, well, the cost of another level of indirection is often performance. We don't really want to burden method invocation with a performance burden, so that is something that we really need to think about. But let's wave our hands and pretend the performance problem was just going to be solved for us by magic, and think about what we would want. Well, what we want is for the static compiler not to emit code to build a Lambda, but to emit a recipe for building a Lambda. I've got a Lambda whose arguments are this, who capture these arguments, whose behavior is over here, right? Rather than spinning bytecode to generate a class that implements that Lambda. And then the runtime would look at the recipe and say, I know a fast way to build that Lambda. I'm going to do it for you. And everything works perfectly, right? But I skipped over the how are we going to make it fast part. So let's drill into that a little bit. So in Java 7, as part of JSR 292, we added a new bytecode, first new bytecode added in many, many years, invoke dynamic. It's a fifth invocation mode for methods. And it's, hello, there we go. And what it does is lets the language runtime have more control over invocation behavior, while at the same time giving the runtime an opportunity to get out of the way so that once things are set up, it can be fast. Okay, so there's this sort of like lie that we've been telling the Java community for many years, that the Java language and the Java VM are completely independent of each other. And it doesn't take a lot of time with the JVM specification to realize that the semantics of invoke virtual are very tightly tied to the inheritance rules for virtual methods in Java, and similar for many other aspects of the JVM bytecode. So, the behavior of invoke virtual, invoke static, invoke interface are fixed and Java-like, great for Java, not so great for Ruby, right? So, without invoke dynamic, compilers like JRuby had to resort to tricks either like reflection, which is really slow, or generating a lot of adapter classes on the fly, which is faster than reflection but has other problems. But the basic problem that we have is that languages other than Java needed a way to say, this is how you resolve a method call in my language. When I say a.b, and B is some method on A, I don't necessarily just want you to use the Java rules to look B up. I want you to use my rules. So the idea is we want to allow some, let's call it language logic, to be plugged in to the call target resolution process. Say, okay, in this context, A.B resolves to that method over there. And then, and here's the tricky part, we want the language logic to get out of the way, so that then the VM can say, all right, you answered my question, and I'm not going to bother you again, and now I can inline through it and all of that. So the idea, and this is sort of a very grand idea, and it's a work in progress, is that the language and the VM become partners in method dispatch, but the language is able to communicate enough information to the VM to know when the VM doesn't have to keep asking the language for help. Okay, so if you're executing Groovy code or Jython code or JRuby code, you can implement the semantics of what does method dispatch look like in your language, translate that to something that the VM can understand, and then it turns into one of the regular old invocation modes. So, the canonical example is, in a language like Python or Ruby, where you don't have types, static types on your variables, and you say, well, the add method takes A and B and adds them. And A might be ints, A and B might be floats. They may be, I call them with ints now and I call them with floats later. But the reality is, if I call add with 2 ints, the next time I call add, what are the types of A and B most likely to be? ints, right? I'm probably in a loop. I'm adding up a bunch of numbers. I don't want to have to do a type analysis every time I want to add some numbers up. That would be horribly slow. So the way invoke dynamic works is that the language logic says, all right, you've called me with 2 ints. Here's the linkage for plus with ints. And if the next time you get called, the types are ints again, don't bother calling me, just do the same thing. And if they're different, okay, call me back, we'll have another discussion. And so this allows us to win tremendously by not having to relink the call every time it's invoked. We only have to relink the call when something significant has changed. Okay, so this was the motivation for invoke dynamic. And you can see this has nothing to do with the Java language. It has to do with a problem that the Java language doesn't have to solve. But it turns out to be a tremendously useful tool for compiler writers in general. Okay, so how does this work? Remember we said every invoke site has an enclosing class, a method name, and a method signature. The invoke dynamic call has all of those things, and it has some extra stuff too. One of the extra things it has is a bootstrap method. That's basically a pointer to the language logic. And the job of the bootstrap method is to return a linked call site. And the call site that gets returned not only says, here's the target of my call site, but also under what conditions do you have to ask me again to relink the call site. And in the default case, you return what's called a constant call site, which means here's the linkage, don't ever call me again, inline through it as much as you want, we're done with this conversation. So that's really nice because then once the VM knows the linkage target, it doesn't have to remember that this came from an invoke dynamic. It can say, oh, I will just always link it to this target, or I'll always inline through to this target, and the language logic gets out of the way. So the extra operands that invoke dynamics gets is this bootstrap method, like I said, the same dynamic argument list that every invocation call site gets, and then an extra set of constants, which you can think of as a static argument list, which is provided to the bootstrap method. Okay, so there's a lot of ways to pass information to the bootstrap. There's the static argument list, and it also gets to see the arity and static types of the dynamic arguments. And so we can use this information actually to implement lambdas in Java, as it turns out. So, all right, so theoretically, if invoke dynamic is meant for dynamic languages, why is Java using it? I mean, after all, Java is a static language, right? It's statically typed. Java is not a static language. It's a statically typed language, but it's a dynamically compiled language. There's a lot of dynamism going on in a JVM. It just doesn't happen to bubble up to the type system that the user sees. So the dynamism here is in our code generation strategy. We wanted to use an extra level of indirection to delay binding to a code generation strategy. So the static compiler emits a recipe for here's the characteristics of the Lambda that I want, and what's dynamic is what happens at runtime, which is what code generation strategy do I use. And we've already identified 2 of them. I could generate an inner class, or I could use method handles. There's a whole bunch of others I could use. I could use dynamic proxies, although why would I, because they're so slow. Or maybe I could use some VM private API for constructing objects out of lead and raw bits. I have a lot of options if I don't have to commit to an interface. If I'm just trying to generate code at runtime, I can do whatever I want, whatever is fastest. And by having this be a runtime behavior, the bootstrap method, is part of the JDK. It's part of the JVM implementation. I can delay the choice of what code do I generate till runtime. So before we had this choice of, should we use inner classes, should we use method handles, was a nasty choice because it carried with it a consequence of interface. Now, by doing all of this behind an invoke dynamic, we've separated the binary representation from the translation strategy, and this choice becomes a pure implementation detail. Okay, so there's that other level of indirection for us, and the fact that invoke dynamic only calls the bootstrap once in the default case, and then lets the language logic get out of the way. That's how we're making it cheap. So we embed this recipe for constructing a Lambda at the site where we have to capture a Lambda, in the generated bytecode. Okay, so that recipe includes desugaring the Lambda to a method. and we pass to the bootstrap a method handle for the behavior. You know, when someone invokes this lambda, go call that method. The functional interface, predicate, mapper, runnable, callable, that we're converting to, and any values that are captured from the lexical scope, like the min age in our example, plus additional metadata that the compiler might know, like, gee, this lambda should be serializable. Remember what I was saying this morning about serialization interacts with every language feature? I would say we spend about 30% of the effort of Lambda figuring out how to deal with serialization. What a waste of time. I want that time back. We actually came to a fairly good answer, but oh my God. All right, so a little bit of terminology here. When we want to create a lambda, we emit some bytecode to capture a lambda. We're going to call that call site the Lambda factory, and that's an invoke dynamic call site, which is when you invoke this invoke dynamic, it gives you back the lambda you're looking for. All right, and so the first time we execute that Lambda factory, it goes and does a bunch of work, links the call site, and then returns us an instance of the functional interface we want, predicate, runnable, whatever, and then subsequent invocations are going to bypass the linkage path and just go through the faster code path. Okay, so let's look at some bytecode. So again, same, pretty much the same lambda, gets desugared to a method whose arguments list matches up with the argument list of the functional interface type, plus an extra argument for this captured value. Okay, so that's step one. So we construct, construct this method. The shape of the argument list, is constructed according to a defined procedure. If it doesn't capture the instance, if it doesn't use this in any way, we can desugar it to a static method. We can almost always desugar it to a private method. So that's that's clean. Sometimes a method, a lambda, will capture the receiver. It'll reference a field. It'll invoke super. It'll do something like that. Then we desugar it to an instance method. Okay, pretty straightforward, and the call site ends up looking something like this, where so this is the source code. What we do is we have our Lambda factory, which is an invoke dynamic. The bootstrap is what we call the Lambda meta factory. That is a method that lives in Java lang invoke. It's part of the JDK. The static arguments we pass in are the target type we're converting to, and a method handle for the implementation down here, and then there are also some dynamic arguments that every invocation receives. In this case, we're passing the captured value as a dynamic argument. So we call the Lambda factory. It hands us back a predicate, and then we just pass that to remove all. Okay, so this is what the static compiler emits, and that's actually pretty straightforward. It's not so bad. There are some optimizations that we can do here. For example, if the set of dynamic arguments is empty, which is very common, like a predicate where string is not empty or something like that. There are no dynamic arguments. We can do some extra optimization where we say, you know what, we only ever have to make one instance of this object, and then we always return the same instance. And so the little trick that people do, like when you're writing a comparator, instead of passing it inline to sort, you say private static final comparator C equals, so it gets run as part of a static initializer, right? We've all done that, right? VM does that for you for free automatically now. Okay, the VM figures out whether you could do that, and if you could, it just does it for you, and it's lightning fast. Okay, so what happens behind the bootstrap? Well, we've got all of these choices. So one option, which is what's going to be our first, our first version, this is probably the one that will ship with 8, is, well, we'll spin the same class, inner class, the static compiler would have spun, but we'll spin it at runtime. And this does have some of the disadvantages that the inner class approach has, because we're generating basically the same bytecode, but it has the advantage that we're not stuck doing this forever. And then we link the Lambda factory site to the constructor of that inner class, which just by absolute coincidence, their argument lists have exactly the same shape as the dynamic arguments of the capture. And like I said, this will be our go forward strategy. Another strategy we could pursue is to have, we'll spin one class per functional interface, runnable $wrapper, callable $wrapper. And the constructor for that would take a method handle, and their methods would invoke that method handle. And that's also a perfectly reasonable strategy. It would result in fewer classes. We will probably get there. We're not there yet. There's also lots of other things we could do. We could do dynamic proxies, which we implemented, and they're unbelievably slow, but at least it proved that you can do it. Method handle proxy, similar, or some kind of VM private, object alchemy. Lots of things we can do here. And in fact, we're free to change this translation strategy from release to release, from run to run, from Monday to Tuesday. It's completely an implementation detail. Okay, so let's step back and look at what we got out of invoke dynamic. So in the case of non-capturing lambdas, like I said, we have this optimization we can do where we just create one instance and always return that. It's a very common case. Probably half the lambdas capture that we've seen in examples capture nothing. It's something that people have been tempted to do by hand. We don't have to do this by hand anymore. And you can think of the call site that's managed by invoke dynamic as a lazily initialized cache. So if you never use it, it doesn't cost anything. We don't have to load the class. There's no bytecode. There's no static footprint. There's no field. There's no static initializer, any of that. And then once it's initialized, stateless lambdas get this lazy initialization and caching absolutely for free. So we've used invoke dynamic now for a couple of things that it wasn't really designed for. It was designed for dynamic languages. This is a statically typed language. It wasn't really designed to be a caching tool, but it turns out to be a darn good one, so we're going to do that. Okay, what else did we get out of invoke dynamic? We got the ability to procrastinate, which is always good. So we deferred the choice of how are we going to generate code for our Lambda to runtime, where it becomes purely a VM implementation detail and can be changed, like I said, from Monday to Tuesday. So now we stamp our binary protocol in stone, which is the call site invocation protocol for this meta factory, and we do not have to stamp in stone the choice of code generation. This is consistent with a sort of general trend of the more decisions you can move from compile time to runtime, the better quality decisions the VM will be able to make. So dynamic compilers, dynamic runtimes make better decisions than static compilers do. So let's move as much of that work as we can to the VM. And like I said, this gives us flexibility. We could use a different strategy in hotspot than IBM uses in J9. That's fine. We can compete on performance. That's fine. Okay, what else? Every problem is soluble by one level of indirection. Well, Indy is our indirection aid. So we deferred the code generation strategy to runtime, but we're not paying the price of that on every call. We're only paying the price of that on the setup. The meta factory only comes into play once per Lambda capture site. And like I said, in the non-capturing site, the non-capturing case, subsequent captures cost us nothing. Just VM optimizes it down to a constant load. And in the capturing case, the subsequent capture cost is basically invoking a constructor. So the way to think about this is, in the bad case, it's exactly as bad as the old way. And in the good case, it's way better. That's what winning looks like. Game theorists call this a dominating strategy. The worst case is just as bad, the best case is better. That's a dominating strategy. Okay, so let's look at performance costs. So there's really three layers of performance costs in this in a translation scheme. There's the one-time cost of linking the call site. There's the cost of capturing a Lambda, and there's the cost of invoking the Lambda. I have data for one of these, but imagine we had chosen the inner class strategy. These would map to the linkage cost is loading the class. And don't forget that loading an inner class has some cost. You have to go to the file system, read bits off disk, and then load them as a class. That takes a lot of work, right? And so what we're doing now is we're doing some computation to dynamically generate a class, which may or may not be slower than going to disk and getting them. And then we're loading that class, which is exactly the same as we were doing in the other case. The capture is invoking the constructor. In the default translation strategy, we link the call site to the constructor. So that's the same. And presumably the invocation cost is the same as well. Let's take a look at some capture costs. These came from our performance team. So we ran this on a monster machine, 4-socket, 10-core Nehalem server, so 40 cores, 80 threads. So these numbers are in operations per microsecond. And we have three cases here. This is the just plain old make an inner class and capture it. This is the make a lambda that captures nothing, a stateless lambda, and this is make a lambda that captures one variable. And the columns are run it in single thread mode, run it on all the cores, and then divide the multi-core by the single core to give you an idea of how this scales across cores. So top row is old way, the way we would do it today. We were able to get 160 instance creations per microsecond. So what is that? About 6 nanoseconds per invocation. And running it on multiple cores, we maxed out at about 9x before cache effects started to get in the way. In the Lambda case, what we saw with the non-capturing Lambda, which is basically caching the Lambda at the invoke dynamic call site, we saw in the single-threaded case a factor of 4 improvement in throughput. That's great. In the multi-threaded case, we saw a factor of almost 20 improvement in the multi-threaded case. And the reason is, over here you're doing allocation. Eventually allocation starts to contend with activity in other threads. Here we're not. All the cores are running at full machine speed. And then in the unfortunate case where we fall back to where we have to capture something, it's exactly as bad as the old way, both in the single and multi-threaded case. All right. So these numbers bear out the theory that the best case is much better, the worst case is just the same, and we still have room later to pursue. I mean, this is just the dumb strategy. We're just starting with the dumb strategy. There's room for us to get better. So I think this demonstrates that the approach we're taking is already a huge win and has a lot of headroom. Okay, so this is great for Java. It's also pretty useful for other languages. Okay, so this is a mechanism that we're delivering not just as a Java language feature, but the runtime support for this, the Lambda Metafactory, is going to be part of the JDK runtime. It'll be code that lives in Java lang invoke. And yes, the semantics are tailored to the needs of the Java language, but if you're writing JRuby code, there's a good chance that you're going to want to call libraries in Java. Those libraries in Java may want to take lambdas. Your clients may want to pass lambdas to them. And so what this does is if you're the JRuby compiler developer, this gives you a path to say, all right, I'm calling this Java library that, and I want to pass a lambda to it. Why don't I use the same JDK runtime code to generate that lambda that the Java compiler would instead of generating my own code? Right? Because compiler writers are lazy just like the rest of us. So if the runtime can do it for you and can do it efficiently and will get more efficient over time, why wouldn't you do that? So given that Java APIs will be full of these functional interfaces and other languages want to call them with their own closures, and we're likely to improve the performance of this runtime facility anyway, it's a pretty good move for JRuby or Jython or Nashorn or any language on the JVM to take a look at this as a way of converting closures to functional interfaces. Certainly better than spinning your own inner classes. Okay, how could this get better? Well, we've looked at a lot of VM optimizations that we can make to make this even better. So right now, the big cost is capture cost, right? It's still, the slide we showed before showed that we've done a lot of work to get that capture cost down, and we're not at all concerned about capture cost in the case of, here, take this lambda and call it for every element of a collection, because the capture gets amortized over many invocations. But let's say the lambda is one where it might never get called. Here, take this lambda and call it if there's an error. We would rather not pay that capture cost if we're never going to invoke the lambda. So what could we do in the future to reduce that capture cost in those cases? Well, it turns out we've done a lot of work to make the capture semantics and the signature of the Metafactory very simple and map directly to method handle algebra so that the the VM can recognize those things and intrinsify them and say, oh, yeah, I see you're doing invoke dynamic, but I see that the bootstrap is Lambda metafactory, and I know the semantics of that. That's really these method handle semantics that I already understand. And I happen to know that a Lambda capture is a pure operation. So I can reorder it with other operations. I can do code motion, push, and push it into a called method, and maybe avoid having to do the capture at all. Similarly, you can think of Lambda capture where we take a method handle and turn it into an instance of a functional interface as being a little bit like boxing an int to an integer. And there are optimizations that we can do. Hotspot is not as good at them as JRocket was, for example, but we're getting better. Is to optimize box unbox by moving the box operation closer to where the unbox operation are, and then they annihilate each other in a matter-antimatter collision, and the costs go away. So we could apply the same the same optimization. If you're passing a Lambda to a method, you inline through the method, you do escape analysis on the boxed object, you discover it doesn't escape, you do code motion to move it where the invocation is, and then you eliminate the box unbox, and it becomes a straight inlineable method invocation, and the cost goes to 0. So we don't have this done yet, but I don't want to say it's rocket science, but it's not rocket science, right? I mean, like, all this VM stuff is rocket science, but like, our rocket scientists know how to do this. So it's not like we don't know how to do it, we just haven't done it yet. So this is a pretty nice future, and like I said, if other language compilers generate calls to the metafactory to do this, they'll get all this for free. So pretty cool. All right, so like I said earlier in my first talk, no language exploration is complete without beating your head against serialization. It's just a fact of life with Java. It's like, every job has bad things, this is mine. Serialization interacts with everything. And the reality is, if you write code like this, you have some functional interface foo, it extends serializable, you take a Lambda that does something really trivial and say convert it to foo, everyone's going to expect this to be serializable and they're going to be right. And if we made it not serializable, we would be jerks. And we don't want to be jerks. So we have to make this work. Well, the class associated with foo here is dynamically generated. So we can't just serialize that because it won't exist when the user goes to deserialize it in the other VM. And even if it did, the other VM might be using a different translation strategy. And so it can't just deserialize the implementation. It has to rebuild it up from the recipe. And so just as we have a dynamic translation approach, we need a dynamic serialization approach. And we need to do that without exposing new security holes because these methods, Lambda bodies get desugared to private methods, but we don't want to open up yet another way that serialization might let you call private methods that you're not supposed to. So, a lot of pain here. So the approach is, we represent a Lambda by its recipe, where it has a behavior method handle, a class that we're converting it to, some static metadata, et cetera. And so what we can do is we can use the existing hooks in serialization, read, resolve, write, replace, to intercept serialization and instead serialize the recipe. Okay? And we write out a serialized instance of the recipe so that when you deserialize it, it reconstitutes the Lambda from the recipe. So it turns out we use a separate metafactory for that, mostly so that we can keep the fast path simple, so we can enable the optimizations I talked about 2 slides ago. And then at deserialization time, we reconstitute the Lambda from the recipe using whichever translation strategy we're using now, which could be different from the one that originally created the Lambda. So this is actually pretty cool. It works. You can make a Lambda on a VM that uses translation strategy A, deserialize it on one that uses strategy B, and it still passes all its unit tests. It's really cool. I would have rather spent the time on something else, but thank you, Jim Waldo. So all right, summing up, invoke dynamic is your compiler writer Swiss Army knife. It is a great tool for doing almost anything. So if you're a compiler writer, You definitely want to give it a look. We're using it in the Java language to give us flexibility over translation strategy and without sacrificing performance. And using this, even using just the dumb translation strategy that we chose, is still dominates the inter-class strategy completely performance-wise. And so that's a really good starting position, and it'll of course only get better. Few places to go for more information. The Project Lambda page has all kinds of documents about what we're doing about Lambda and Java. There's a specification draft that you can get at. There's a sort of easy to read overview, and you can get binary builds off of java.net. All right, well, thank you very much.